Hi, I'm Susan Oldfield,
I'm Morgan Rollins.
I'm Gabby Gordon.
and we're representing the Temple University COVID assistance team. And we are here today to do a webinar for you regarding 3D printed face shields and how to make them at home. Now, there are a variety of different sources you can use to get a design for a 3D printed face shield. What the TUCAT shield really brings is that it's a little bit more durable. It's designed for repeated use after it's been treated with epoxy, which we're going to go over later in this presentation. It's also a little bit heavier, so it can work with thicker plastic, which a lot of other shields will just fall off your head if you use thicker plastic, and that was actually what motivated us to make our own design. So the requirements to make this are quite simple. It just needs a standard 3D printer, the personal kind you might have at home, a 3-hole punch, standard American, a piece of sandpaper or a hand file, a pair of scissors. You will need filament. We're recommending PETG, and we'll go into that in detail shortly. You will need epoxy resin, plastic sheeting, and high-density closed-cell foam, which we will also be going over later in the presentation.
Hi guys, so my job here is to talk to you about the printer recommendations, and a little later I'll go over the specific filaments that we went through and why we chose PETG. So to get us started, we'll talk about the printer and what are some of the requirements needed. So as you can see, the first thing is the print bed dimension. So mine is 150 by 230, and I was still okay to print it, even though 150 was stretching it. So it's there's a little bit of wiggle room, but if you think about it, if it's too big, then the piece will just fall off, or the slicer will not let you print it. But if it's big enough, you're perfectly good to go, and you could just crank a bunch out in overnight or just in an afternoon. So, and this is all for one print at a time. So the two printers that we looked at were FDM and the laser printers. And we chose FDM because they're way cheaper and a lot more people have them. So hopefully this will reach a lot more people and you'll be making them at home. What an FDM does is it melts plastic and lays it down layer by layer. So that's just a little bit of background on that type of nozzle, on that type of printer. So what we chose to do was an 8mm nozzle. The typical nozzle that comes with the printer is a 4mm. And we chose this for a reason. As you can see in the bottom left of the screen, the nozzle diameter makes a very big impact on the time it takes to print a specific volume of filament. So something we found is that in 30 minutes, you can print a face shield with an 8mm nozzle, but in 2.5 hours, you can print it with a 4mm nozzle, and so it's way more than twice as fast to print it with an 8mm nozzle. Now, there are give and takes here. The 8mm nozzle does ooze more. It does take some tuning to change it over from a 4mm nozzle. But if you're willing to put in the time, the extra 30 minutes to tune this all up, it's definitely worth it. You can print more, considerable amount more. So filament recommendations. Here, this is what I found the most interesting. This chart is from a website called Simplify 3D, and you can find links to that website over on our website. A lot of the troubleshooting does take you over to this website because it's a great source. It walks you through with pictures and is very helpful to everyone from beginners to experts on 3D printing. So we decided to collect the information for the 4 most common filaments. That is ABS, flexible filament, PLA, and PETG. So flexible was never even a consideration for this project. We just decided to put it in there so you could see its characteristics compared to the others, as it is an important filament in the 3D printing world, and it's fun to work with. So we thought you guys would like the knowledge. So before wasting any more time, here we go. So the strength. this is how much force it takes to break, and that's definitely important. So flexible, not very strong. ABS is decently strong. PLA is very strong, and PETG is average. It's medium strong, we should say. So you can't just say, I want the strongest material done. There's, again, give and takes. So PLA, even though it's the strongest material, it's very stiff. And that's something that'll make this mask very uncomfortable. It won't be able to conform to the user's face. It won't be able to, give a little bit. And so that was a big downside to using PLA. ABS is less stiff, so it's both ABS and PETG are 5 out of 10 on the stiffness scale. So they both can give a little bit, but they're not very flexible. I wouldn't consider them a flexible filament. They can move a little bit more, which makes them more durable. Because if you have a stiffer material, it's going to be able to break easier. It's going to be more brittle. So you can see that in both ABS and PETG. They're very durable, and flexible is the most durable because it's the least stiff. Kind of give and take. So now it seems like we have narrowed it down to ABS and PETG. Price, PETG is a little bit more, but it is worth it in the end for what we're about to tell you. So the extruder temperature is important, and again, ABS and PETG are kind of similar. PETG is a little bit higher, but even people who had a maxed out printer around 230 were able to print it around 240 or 250. It just took a little extra finagling. Bed temperature is also quite important because you want to get that correct, and we'll go into that with troubleshooting, because if you don't get it correct and spot on, the print will peel off, or the first layer won't adhere at all, and you'll end up with a failed print or warped print, which is also failed. But finally, we want to go into printability. We wanted to choose a filament that is easy to print for our users, because no one's going to want to spend hours just trying to get the single filament to print and then not be able to get it to print and not be able to help anyone by making these shields. So printability and accessibility are very important. And between ABS and PETG, we decided to do PETG because it is a little bit easier to print than ABS, because it's not required to have an enclosure. ABS is highly, highly recommended to have an enclosure due to fumes, and it's easily warped. PETG does not warp as much as ABS, although it does warp, but not as much, and it doesn't require an enclosure, though it helps. So the last positive to PETG that made us choose it was the post-processing technique that we could use, and Gabby will go into that. So
it should definitely be noted that all filaments used in this style of printing will be porous. There's no filament you could use that wouldn't be porous. So no filament could be used untreated in a medical setting and be cleanable. And anything that a printer can print can't be autoclaved, because autoclaves are just too hot. So none of the filaments, we're going to avoid those downsides, and they are things that we will be taking into account later in the presentation. So printing. How does one, so most people setting upon this will have printed things. We're trying to make it very easy to access the file. You can go to tucat.temple.edu, and this link will take you right to our face shields page. If you're on the website, you can go here to 3D printed face shields. As you see, we've got the instruction manual and all the files that you will need. The basic frame is available here. We also have a file for printable elastic clips. Now, these are optional, and they make it a lot easier to adjust the tightness of the mask. They go on the sides of the headband, and the elastic goes through this hole and then is tightened with these little teeth. The reason why we decided not to do them for mass production was because they are quite finicky to print. It's recommended that you use a 4 millimeter nozzle, 0.4 millimeter, sorry, the smaller nozzle size. while it's better to print the face shields with a larger nozzle size. So if you want to make these, they take a little longer and they require that level of extra detail. And if you only have one printer, you'd be swapping back and forth. So that's less than ideal. It's also, no, I guess I covered that. Okay, so yeah, you'd have to be swapping and it needs more detail. So it didn't work out for us with mass production, but if you're making fewer shields, you may decide that this is something you want to go forward with. I included them in the print platter that I will be showing you shortly. We also have the file for the laser cutting for the foam inserts. If you have a laser cutter, you can batch make foam inserts using this file here. If you do not have a laser cutter, we have included a hand template so that using an X-Acto knife, you can, using an X-Acto knife, you can cut out the foam insert by hand. And so for small scale operations, that will be perfectly effective. So Frame STL, you would download by clicking that button and put it into whatever slicer software you are most comfortable with. I have a Prusa machine, so I like to use the Prusa slicer. As you can see here, we have the headband and the 2 clips. My machine has a 0.4 nozzle, and I was never able to upgrade it. We transitioned so quickly to the cast-based production that it didn't seem worthwhile to upgrade all the printers. Also, Prusas can only accommodate up to a 0.6 nozzle. They don't actually go up to 0.8. So with the 0.4 nozzle and a 0.2 layer height, I can print both the face shield and the clips in one go. It will take a little while. In fact, let's click slice now. It will take 3.5 hours to do this at a 0.2 layer height. I had tried making shields with a higher layer height, but another reason to go for a larger nozzle is that with a 0.4 nozzle, you can't really print larger than 0.2 and get good results. If I print with a 0.3 layer height, I get something like a wicker basket, and that's not going to cut it. So the other things you will want to think about, you want to think about bed placement. Prusa has a button that gives you the most efficient bed placement for your objects. Makes it take the least time, make sure nothing's touching each other. That's ideal, but you may have to do that manually depending on the software you're using. Another thing to keep in mind is perimeters. So if we go to the sliced view, you can see that the perimeters are in yellow while the fill is in red. Well, purple, magenta, let's say. So this is a 2 perimeter, which is the default for Prusa. You may find it's got more flexibility with more, if it isn't all square like a waffle inside. If you have more perimeters, you will have a more flexible print. So what I actually did for mine was, I believe I settled at 6. And so I updated to 6 perimeters. And as you can see, we now have a lot more yellow and a lot less magenta. And that optimized my print. It actually takes a tiny bit, well, it does take longer. The print time is now up to 4 hours and 17 minutes. So you're going to have to want to balance that extra durability created by the additional perimeters with the amount of time you have to print. I certainly recommend trying a few different ways and finding the right balance for you. All the printers are going to be different. The work environments might be different as well. So I believe I have now covered most of these things. I went with a 20% infill, but really 15 is fine. The infill is not particularly important for this. That is not where the print is getting most of its strength from. There are a lot of issues you may run into in your print, and Morgan is going to walk you through some troubleshooting.
Yes, so troubleshooting. I did a lot of it. So let's start off with bed adhesion. That is something you're going to run across no matter what filament you're going to be printing with. If it's PLA, ABS, whatever. So PETG is infamous for over-adhesion. This means that it's going to be hard to get off of the plate. There's been horror stories of it peeling up pieces of glass or pieces of your specialty plate, and then you have to buy a whole new plate, which not fun. Nobody wants to put the money into a new plate when yours is perfectly good. So a very good solution I found to this was just blue tape, blue painter's tape. And actually I have
Back in the distance of the Ideas Hub.
Yeah, there you go. There's the Ideas Hub. So this was $6 on Amazon, and it's just a 6-inch roll of blue tape. You can see my printer back there if I go like that. So yeah, I highly suggest that, because then you just roll it out, put it on the bed, and you're done. You don't have to make sure none of the tape is overlapping or anything. And so if you don't have that, that's fine. You can use normal blue tape, but when you're laying it on the bed, make sure that the edges are touching each other, but they're not overlapping, because that will cause an error in your print. So that solves overadhesion. On the flip side, you're going to have underadhesion. Some causes of this can be the bed temperature, the nozzle temperature, the extrusion multiplier, so many things. There's not one specific reason that there's going to be underadhesion. But some solutions include, like I said, you can dial in your bed temperature to get the first layer right. And you can also dial in your Z height. And obviously a lot of these problems can be solved with making your bed level. So make sure to do that before you print. But your Z height is also very important, because if it's too small, if the distance between your nozzle and your print bed is too small, then you're just over smushing the plastic down, and the filament is going to stick to the nozzle. You want to have, for PETG, you want to have a larger Z height, because it tends to stick to the nozzle, ball up, and I'll get into a little solution for that later. But if you get the right Z height, then you'll lay it nice and get a nice width as well on the print bed. And that can be set during using the Z offset, or even manually by adjusting the height of your bed. Either or works. So the next big issue is the temperature calibration. So that is quite important, because if your filament is too cold, then the filament will grind and not extrude. But if it's too hot, you're going to have over extrusion, and this can cause inaccurate prints, because your printer thinks you're printing let's say 0.4 millimeter width of filament, but it's over extruding because it's too hot, so you're really printing a 0.5. That's an exaggeration, but that's just something for you to think about. And this will cause inaccurate prints. It'll cause blobby prints, so it'll look like your print melted, but it didn't. It'll cause little zits in your prints, which are little bumps. And so you really want to get the temperature right, because you want that layer adhesion to be right, and you want, obviously, an accurate print. So next, we can talk about retraction. PETG is also notorious for oozing. So like I said before, it'll stick to the nozzle and cause a ball up, and what that will do was it'll stick to the top of your print and peel it off, which will cause the print to fail. An easy fix for that is changing your retraction settings. What I found, I have a direct drive extruder, so a 3 millimeter distance at around like 20 to 50 millimeters per second worked for me. I know that's a large window, but it's very different for each printer. So that worked for me. So basically what that retraction does is the extruder sucks up the filament and keeps it there while it's traveling, so it doesn't ooze as easily. So that brings us to extrusion multiplier. This can help with the width, and it can help with dialing your Z height in even more. It doesn't affect the height, but in combination with dialing that height in and getting the temperature right, and this extrusion multiplier, you get the right width of your filament, meaning the most accurate print that you can get. So think of this as the flow rate, how much filament is getting pushed out of the nozzle at any time. So it usually is in the scale of, it's usually a percentage, but in scales of, at least mine is from like 0 to 1 or 0 to 1.5. That's something that it's normally hovering around 1, a little less or a little more, but that's different for each printer. So that's it on troubleshooting. If you need any more help, go to our website on the 3D printing page. There's troubleshooting on the bottom.
Hi guys, so I'm going to talk about the assembly process. So the post-processing procedure begins with deburring the sample using a file or sandpaper. Next, you're going to coat the sample with an epoxy resin layer. This can be accomplished by either brushing the epoxy onto the sample directly or by dipping the sample into the epoxy coating. You must leave the sample to sit for 24 hours before moving. Additionally, you must wait 72 hours before the sample to completely cure before use. The next component is the plastic shield. A 0.5 millimeter PET plastic is recommended. Our face shield was specifically designed for this plastic because it's sturdy enough to handle this material. This material is more durable compared to other plastics. You will start by cutting the plastic to 12 inches by 9.75 inches. Next, you will punch using a standard 3-hole punch. This component is easily replaceable if scratched or dirty. The next component is the elastic band. A 9-inch elastic band is recommended. A wide elastic band with a cloth coating is preferred for comfort. You can also use regular elastic bands if necessary. For the clipless design, you can cut 1/2-inch slits at each end of the band. Additionally, sealing the slits with heat is recommended. This can be accomplished by using an iron, heat gun, or lighter. The final component is the foam insert. This is an optional addition intended for the comfort of the user. Having a more comfortable mask is the difference between the user actually wearing the mask and taking it off due to discomfort. We've been told that this additional component is preferred by those in the field. You must use closed cell foam in order to reuse the component. This is because the open cell foam is unable to be sanitized and has to be discarded after each use. The laser cut design is available on the website, as well as the PDF of the pattern for hand cutting. An X-Acto knife is recommended for hand cutting as well. So this is a video of the assembly procedure. Here we have the plastic. Next is a 3D printed component. And finally is the elastic band with the slits on each end. First, you will attach the plastic to the 3D printed component. And next, you're going to attach the elastic band to either end. And that's it. So really, really simple. And the final step is the distribution process. So you can distribute the shields either assembled or disassembled, flat packed. This choice really depends on who the shields are being sent to and whether they're going to be used right away or after a period of time. It should be noted that the plastic may distort after a long storage period, so it really is best used within 2 weeks.
So before use, these should be sanitized very thoroughly. We recommend completely submerging the entire, the plastic portions in a bleach water or alcohol solution for at least 5 minutes. And that should get a completely sanitized starting place. doctors and nurses can't always do a complete submersion between all patients. Usually we recommend wiping the shield itself clean with 80% alcohol or hydrogen peroxide solution between visits. The band and the plastic can both be completely submerged in isopropyl alcohol. The fabric bands, though, can be sanitized along with essentially the hospital laundry. However, you're sanitizing the other fabrics in the hospital should be fine for fabric bands that are holding the masks in place. The shield headbands have been extremely successful in the hospitals, and we have reports that they've been going for weeks. Single headbands single shield headbands have really been lasting, and any damaged versions can very easily be replaced with just new plastic without necessarily making a new shield. Just another reminder, do not autoclave them. They will melt, and keep them away from open flames, generally a good policy. But the reviews have been really great for the TUCAT shields. We've heard very happy Temple University employees getting back to us about just how valuable these have been. So it was very important to us and the rest of the TUCAT team to make sure that other people could build these, because they are easy to make, and in this crisis, it's important that people have access to the best methods possible to make personal protective equipment to keep our healthcare workers safe. So we hope that this has been an informative webinar. You will be able to contact us through the website if you have further questions. And thank you very much.
Thank you, guys.
Thank you.